Welcome to the Mahatma Gandhi Institute of Technical Education and Research Center. In 2004, a national level institute MGITER has been started in the field of engineering and technology as per guidelines of All India Council for Technical Education AICTE New Delhi. MGITER is approved by AICTE New Delhi, Gujarat State and affiliated to Gujarat Technological University Ahmedabad, which is also known as GTU. Our goal is to be an institute of generative ideas so that we remain relevant to our society. The MGITER has always been an organization on move with continuous effort on improving its processes and to maintain its relevance to the Indian science scenario, with adding new programs in its programmatic portfolio. We strongly believe in overall development of students, so for that we provide them a different platform like state level tech fest, project fair, different sports activity, which helps students to teach teamwork and problem solving skills to get physical health benefits, boost self-esteem and reduce pressure and stress for prove their skills in distinct area. Welcome to the virtual class of design of AC machine. Myself Professor Gaurang Patel from Mahatma Gandhi Institute of Technical Education and Research Center, NAVSARI, from Electrical Engineering Department. So today here we are discuss about the second part of the design of three-phase induction motor, and in my previous video you might have gone through the first part, so where we have calculated the main dimension of three-phase induction motor. Okay, so in today's part we will be moving further with some more details on electrical machine design, that is more over the induction motor design. Okay, so let's see what is the main concern of today's topic. So these are the contents which I am going to cover in today's session. Okay, so first of all we will start with the suitable combination of stator and the rotor slot. So how this combination will be occurred and how it will be affect to the induction motor, and how it will be the effect to the performance of the induction motor when we selected the stator and rotor slots. Then after we will see what is the effect of harmonic field on performance of three-phase induction motor, because the harmonic is a very critical issue in nowadays, because we are going so many control system which are based on the power electronics device, and these are the major components that we can say that create the harmonics or that produce the harmonics in our power system or in our in our electrical equipments. So after once the harmonics is produced, of course we have to eliminate with that. So how to reduction of harmonic and how to reduction of harmonic torque, we will be discuss it after completion of this topic. Then after, what we are going to discuss, that is factor affecting the length of air gap, and finally we are going with unbalanced magnetic pool. Okay, so in today's session it is I hope it is very interesting topic, each and every topic with related to our subject, because this reducing of harmonics, what is the combination of stator and rotor slots, that is the main concern when you are going to design a machine. Okay, so let's begin with the suitable combination of stator and rotor slots, that we will see how it will be affect. Okay, so here some of the conditions for the suitable combination of stator and rotor slots. So when we are going to design a and three-phase induction motor, it is necessary to having a specific stator slot and having a specific rotor slot. So what are the conditions that we, and how these conditions are affect in design of three-phase induction motor, we will see one by one. Okay, so when you are considering the three-phase induction motor, the design of three-phase induction motor, the stator and rotor slots we need to consider. Okay, if rotor slots are equal in number of stator slots, see here SS, which is stands for stator slots, and SR, which is stands for rotor slots. Okay, so if SS is equal to SR, that means stator slots is equal to rotor slots. Then what happens? That at that time one phenomenon in occurs, and this is known as cogging. Okay, so for avoid cogging, what we have to do, we must have to consider, or we must have to uh, identify that SS does not equal to SR. Okay, otherwise the phenomenon called cogging is occur. What is exactly cogging and what is the definition of cogging, we will discuss these things in later in this section only. First of all, you just have in this slide particularly, you just have to focus on what are the conditions when we are deciding the number of stator slots and number of rotor slots. Okay, so first of all, to avoid cogging, what we have to keep in mind, SS does not equal to SR. Okay, so here we see one more phenomenon, as we discussed, that is crawling. Okay, so crawling, the condition of occurring crawling, that is SS minus SR does not equal to 3P. Okay, and as we know that P is equal to pole. Okay, so those conditions are very important in related to the design of three-phase induction motor, as well as this question is also asked in examination as well. They are asked in several ways, like write down the suitable combination of stator and rotor slots, or what are the conditions where stator and rotor slots have decided, or at that time you must have to explain all those conditions in detail. In viva examinations, it's also asked so many times what is cogging, what is crawling, so you able to understand, and if you able to say the answer to the examiner in a convincing way. Okay, so please understand this concept very carefully. Okay, so after crawling, one more phenomenon or one more conditions over here, to avoid synchronous hooks and cups, to avoid synchronous hooks and cups in torque speed characteristic. Okay, so for the avoid hooks and cups in torque speed characteristics, there is a condition, that is SS minus SR does not equal to P, 2P and 5P. Okay, so what they will say, that SS, that is the stator slot, SR, that is the rotor slot, does not equal to P, 2P and 3P. Once again, P stands for the pole here. Okay, so to avoid synchronous hooks and cups, this condition you must be keep in mind. Okay, after that, just a moment. So after finishing these three conditions, we are moving towards the fourth condition, which is also very important, because you can see that in three-phase induction motor, so many times there is a noisy operation is there. So why this noisy operation is occurred, and how this noisy operation can be eliminated through fulfill this condition. So to avoid noisy operation, what you have to keep in mind, the condition is given over there, that is stator slot minus rotor slot does not equal to 1. it does not equal to 2. Two more conditions are also there, that is p plus or minus 1 or p plus or minus 2. So those are the condition to avoid the noisy operation. Okay, so these four conditions you have to keep in mind where suitable combination of stator and rotor slots have been asked in your examination. Okay, then finally we can conclude that after this discussion we can say that SS minus SR, that is stator slot minus rotor slot, does not equal to 0, plus or minus P, plus or minus 2P, plus or minus 3P, plus or minus 5P, plus or minus 1, plus or minus 2, and P plus or minus 1, P plus or minus 2. Okay, those are the conditions which we have to must keep in consider in our mind when stator and rotor slot combination have been selected. Okay, and then next further we will see over here. Okay, uh, so those are the condition it has to be satisfied while choosing the number of stator and rotor slots. So if these conditions are satisfied, then only the motor will work properly. Okay, otherwise the problems will occur, and what those problems are that we have seen now, such as a cogging, crawling, and then synchronous hooks and cups. Okay, so in torque speed characteristics, noisy operation is also there. So the problem associated, if number of those all the problems are associated with the selection of number of stator and rotor slots is not chosen if it is not chosen properly. Okay, so then after that we are going to see over here another concepts, that is the effect of harmonics. Okay, so over here, effect of harmonic field on performance of three-phase induction motors. Okay, so what is the effect of harmonic field on the performance of three-phase induction motor? We will see it. Okay, so over here we can see something interesting, that is will be calling it as calling as the picked up harmonic field on performance of three-phase induction motor. Okay, when we are thinking of induction motor, what we need to understand that harmonic field is present in induction motor, harmonic field is produced in induction motor, and what is the nature, how it is going to be affect exactly on the performance of the motor, that we need to discuss over here. So first of all we will starting with the cogging. Okay, over here cogging, you can see on the effect of cogging over here, it is say that refusal to start, due to the cogging it is refusal to start, and magnetic locking is there. So here we discuss the details why cogging is there and why it due to the cogging three-phase induction motor is refused to start when cogging is happen. Okay, so harmonic field basically the phenomenon which occurs is related with the number of stator and rotor slots. So first of all we will start with the first part, that is say cogging. This is the effect of harmonic field on performance of typical induction motor. Okay, so by mistake if you take a number of slot, SS is equal to SR. Okay, if you remember the condition is what, to avoid cogging, that is SS does not equal to SR, that is stator slot does not equal to the rotor slot. But by mistake if you chosen the stator slot is equal to SR. Okay, stator slot is equal to SR if you chosen by mistake, then what's happen? Okay, then in that case there is a magnetic interlocking between them. Okay, if you don't satisfy this condition, then magnetic interlocking will be there. How magnetic interlocking will be there, we will see over here. Okay, so the magnetic field of stator and magnetic field of rotor. Okay, if you consider over here, there is a stator and inside of there is a rotor. Okay, so there is a certain winding on stator as well as there is a winding on rotor as well. I just drew it over here for the understanding arbitrarily. It is not the exact what it is. The winding will be there. Okay, so due to this winding, magnetic field is going to be produced on the stator and rotor. Okay, so when the stator slot and rotor slot are equal, then what happened? The magnetic field produced from the stator and magnetic field produced from the rotor are equal. Okay, if slots are equal, then number of turns are equal, so definitely there is a magnetic field produced in the stator and rotor are, we can say it is the same, but in nature they are opposing to each other. The rotor magnetic field and stator magnetic field, it is opposing to each other. Okay, so when it is opposing each other and if it is same in magnitude, keep in mind that when it is opposing to each other, okay, if you consider that is the stator magnetic field and that is the rotor magnetic field, if it is SS and then you consider it is rotor, you consider this is the direction of rotor magnetic field and this is the direction of stator magnetic field, but it is opposite each other. Okay, if the stator slot is equal to rotor slot, so what happen if it is opposing each other, then motor will refuse to start. Okay, because we know that if the magnitude is same, definitely the motor will refuse to start and the magnetic interlocking occurs between the stator and rotor. Okay, and we are calling that as a cogging. So this is the effect of harmonic field, how it exactly happens or how it exactly the harmonic field is produced, that also we are going to see in the next slide. Okay, apart from that, there is one more phenomenon called crawling over here. Okay, so I hope you understood what is cogging and why it is happen when the condition SS is does not equal to SR, that if it is not satisfied. Okay, apart from that, one more phenomenon that is known as crawling. Okay, so what happen in crawling, that is a rotate, motor will rotate at sub-synchronous speed over here. Okay, it will be rotate at sub-synchronous speed and produce noise and vibration. Okay, just a minute. So just a moment. Okay, so when we are going to discuss the crawling, two factors we have to keep in mind, that is one is NS, that is known as synchronous speed, and one more thing, that is the small, that is a capital letter NS, then and there is a small ns, which is known as sub-synchronous speed. Okay, it is known as sub-synchronous speed. Okay, so now here what we are going what I am trying to make you understand, that is when capital NS, that is synchronous speed, okay, and the small ns, that is the sub-synchronous speed, if small ns, that is sub-synchronous speed, is less than the synchronous speed, at that time crawling is happen. Okay, and at that time you can see your motor will going to rotate at the subsynchronous speed, and when it will be rotated at subsynchronous speed, the noise and vibration will be there. Okay, after that, after the crawling, we will see that is the harmonic field is produced due to the factors of winding, selection of slotting, saturation, and uneven air gap, etc. So if we discuss this phenomenon in detail, we have to actually see that the synchronous speed of the motor, which is what we need, the motor is going to be run at the synchronous speed, but due to the crawling it will not happen exactly. Motor will run at the subsynchronous speed due to the crawling. Okay, so when we can say that harmonic field which is produced, the part we are talking is about the harmonic field performance or effect of harmonic field on performance of induction motor. Okay, this harmonic field is generally due to the problem with the winding slotting. Okay, I already discussed this topic. This harmonic field produced due to the problem of the generally selection of number of slotting that we provided. Okay, if number of slots are not provided exactly, then magnetic saturation which occurs in the core, okay, and uneven air gap will be there. Okay, so these are the causes of production of harmonic in harmonic field in the induction motor. Okay, so due to these problems, mainly winding slotting, saturation, and uneven air gap will be there. Okay, so due to this problem, what happens? Slotting, saturation, and uneven air gap will be there. Okay, so if this harmonic field is produced, this field induce the EMF in rotor winding. Okay, what happens if this harmonic field is produced over here? So you can see this field means the harmonic field induced EMF in the rotor winding and circulates the current which causes losses. Basically, we need to understand that the basic phenomena whenever a magnetic field is present, any magnetic field, you can consider any magnetic field which is present, and if you place a current carrying conductor in that magnetic field, we know that that the flux is cut by the conductor, may not be current carrying conductor, but this could be a conductor which is placed in a magnetic field. If magnetic field is alternating in nature, likewise, then what happens? Due to that alternating nature of magnetic field, a conductor is placed here. Okay, then flux is cut by the conductor and EMF get induced. Okay, due to that EMF get induced. Okay, so if we remember about the rotor of induction motor is generally short circuited. Okay, if you remember, rotor of induction motor is generally short circuited. If it is short circuited, it means it has a closed path of current flow. Okay, so over here you can lightly remember that is the phenomenon of, or you can see it is the principle of general motor. Okay, if we providing the closed path, that current is circulated in it. Okay, so we could say the magnetic field which is produced here is that it is a harmonic field which is produced. The harmonic field will introduce the EMF in rotor winding. Okay, so it is here the reason to introduce the EMF in rotor winding, that is the harmonic field. Okay, so it is very important to understand. A harmonic field will produce the EMF in rotor winding, and due to that the current will circulate. Okay, and definitely that is not the natural current. Okay, we need the current to flow in that circuit, but that is not the natural current. This current is due to the harmonic field. Okay, so if this current is going to causes the losses, okay, because it is not a natural current, so definitely it is going to be considered as a losses. Okay, so over here we can see, over here, that is, if 1 minute, okay, so yeah, so the number of pole becomes np instead of p, where n is order of harmonics. If it is happen, the synchronous speed is given ns is equal to 120 f by p reduces. Okay, how it will happen, we will see over here. Okay, so how it will be reduces ns is equal to 120 f by c. We can say, if order of harmonics, say first order, third order, fifth order, likewise that, the number of poles in the motor will increase. What happens if the number of poles increase? We need to think of the synchronous speed ns over here. What we need to think over here? We need to think over here the synchronous speed ns. Okay, so when the synchronous speed ns, which is given by simply 120 f by p, over here the synchronous speed is given by simply 120 f by p. Okay, so what happened here, the f is frequency. Okay, f is frequency, that we all know that. P is number of poles, as rightly we said the number of poles are increasing. So for example, we could take to say one harmonic field is present in the motor. If seventh harmonic is present, if you consider there is a seventh harmonic is present over here. So when we consider, if there is a seventh harmonic will be there, as we discussed right now, that is the equation that is over here, write down for the synchronous speed, that is ns is equal to 120 f by p. F is here stands for the frequency, and p is stands for over here the number of poles you can consider over here. Okay, so what happens if when we are going to consider the seventh harmonics will be there, and as we discussed, that is, and we discussed earlier, that is the number of pole becomes np, or number of poles p becomes increased. Then at that time what you have to consider, if seventh harmonic is considered, you have to consider instead of p over here, you have to consider the 7p. Okay, so what happened over here, if we consider the 7p and number of p is increased, it is going to be, this value, denominator value is going to be increased. So simply it becomes the ns is proportional to 1 by 7p. So if this is going to be increased, so what happened with the ns, what happened with the synchronous speed? Definitely it is going to be decreased. And at that time you can see, if the synchronous speed is decreased, so that means the three-phase induction motor is going to be rotated at some decreasing speed, or this speed you can say this decreasing synchronous speed, which is we consider, or which is we known as a subsynchronous speed. Okay, so that's how the harmonics is affect to the three-phase induction motor speed. Okay, I hope you understand with this explanation. Then we will moving further to the effect of harmonic field on performance of three-phase induction motor. Once we already discussed that if you consider the seventh harmonics, how your speed will be reduced. Okay, now similar things will be happen when harmonics is generated into the three-phase induction motor, and what are the effects of that we will discuss over here. Okay, so over here we can see that. So once again, if we look at over here, we can see that, or we can say that the harmonic field which is produced, it produces two torques will be produced by the harmonic field. I hope everyone has understood harmonic field is the field produced by the harmonics. Okay, so harmonic, those are present all those will be introduced in the induction motor. Why they are produced? That is the reason we have seen in last slide. Okay, so it produces two torque. You can see over here harmonic induction torque, and this harmonic field produces two torques. Okay, first torque out of it, to first harmonic torque will be calling it as harmonic induction torque. Okay, first torque is calling as it is the harmonic, that is first torque is calling is the harmonic induction torque. Okay, so when we consider the first torque, that is known as the harmonic induction torque, this harmonic induction torque is of the order of 7x plus minus 1. This harmonic torque is of the order of 6n plus or minus 1. Okay, so if n becomes equal to 1, then the harmonic of order 6 and 6, it becomes a 6 plus 1. Okay, so harmonic of the order say 7, so if the harmonic of order 6, so order 1, so it becomes the 6 plus 1, this is the harmonic of order 7, or harmonic of the order 5, or harmonic of the order 5. Okay, so how it will work? So if we consider if harmonic order of 1, so due to this condition it is become either 7 or either 5 number of harmonic, that is you can consider that is if it is 7 or either it is become 5. Okay, so with that consideration, say n is equal to 1, we can say the positive moment harmonic for order 7. Okay, and the negative moment harmonic of order 5 will be produced. Due to this, reverse current motor rotates at sub-synchronous speed. Okay, you can, I will make you understand in detail. If you consider the number of harmonic order, that is n is equal to 1. Okay, if either we consider in positive direction, that means 6n plus 1, so it is become 7th order, so it is we consider as a positive order harmonic. And if we take this phenomenon 6n minus 1, so it's become the 5, so this is we consider as a negative order harmonic. That's how the reverse current is happen, or reverse speed will be occurred due to this phenomenon of harmonic rotating in the induction motor, because it is in opposite direction. So definitely if reverse current will be there, so opposite direction of magnetic field will be there, and due to the opposite direction of magnetic field, the speed will be reduced, and which will be considered as the subsynchronous speed of that three-phase induction motor. Okay, now so okay, over here, so it is already explained over here. When the positive moment harmonic or order 7 and negative moment harmonic of order 5 will be produced, due to this reverse current motor rotates at some subsynchronous speed, and this is called as crawling. Okay, this can be avoided if the number of rotor slots does not exceed the number of stator slots by 15 to 13%. Okay, so I hope you understand the definition of crawling and why crawling is occurred. Okay, so as we discussed, crawling can be avoided in the motor. That can be avoided by considering, okay, this is very important statement. This can be avoided if the number of rotor slots does not exceed the number of stator slots by 15 to 30%. Okay, so it should not exceed. This can be avoided. I said crawling can be avoided if number of rotor slots does not exceed the number of stator slots by 15 to 30%. That's what we need to understand out of it. Another torque, as we rightly said, the harmonic, this is the harmonic synchronous torque. Okay, that is the number, that is on number 2. Okay, so the first one is resulting on crawling, that is presented here. The second harmonic synchronous torque, does harmonic synchronous torque, we need to understand over here. If harmonic produced by the stator and rotor are same, when they will become same if number of stator slot is equal to SR. Okay, if it is same when number of stator slot, that is SS, is equal to number of rotor slot. Okay, so what we need to understood, that is, if they are the same in number, then the number of poles and their speed is also equal. Okay, so the number of poles will be equal in stator and rotor. The synchronous speed of the magnetic field will also be the same. So the torque is no doubt opposing each other. The torque produced by stator, over here the torque produced by the stator, if you consider this is our stator and this is our rotor, so if torque produced by stator opposing the torque produced by, this is we consider the rotor torque and this is we consider the stator torque. So if it is opposing each other, hence it results in the magnetic interlocking between the stator and rotor. Okay, so stator and rotor got magnetically interlocked and motor will not rotate. Motor refused to start, so we are calling this is cogging. This situation can be considered as a cogging. Okay, so when the stator slot is equal to the rotor slots SS, the number of straightened poles, number of stator slots and number of rotor slots should be considered equal to the number of rotor slots. And harmonic, those are produced by stator and rotor, those are also same. The torque is same in magnitude, but it is opposing each other. Okay, this torque is, keep in mind, this torque is same in magnitude, but it is opposing each other. So in hence there is a magnetic interlocking between the stator and rotor. So we know this situation where motor refused to start, we are considering the situation as cogging. Okay, this can also be avoided. See, this is interesting. Cogging can also be avoided if what can be done, this can be avoided if the number of rotor slots are not equal to the number of stator slots. Okay, we already discussed it in the last slide, but in this slide we discussed in detail why the magnetic interlocking will be happen and how the cogging can be avoided. Okay, so how the cogging can be avoided? By simply SS does not equal to SR. Okay, so from moving further, we can see how we can reduce the harmonic torque. Okay, we can see how we can reduce the harmonic torque from the three-phase induction motor. So mainly there are the three methods. You can see, that is, first, that is the internal slot winding, chording and skewing. These are the three methods. From that we can reduce the harmonic torque in the three-phase induction motor. We will see three of them in detail. Okay, so as we have seen in last slide, what are the effects of harmonic field on performance of three-phase induction motor? The harmonic torque which produces will causes what is the effective effect. If I ask you the answer, that will be the cogging and crawling. Okay, these are the effects of harmonic torque, right? So to avoid that reduction in harmonic torque, how to reduce that? That can be done by means of three methods. Those are mentioned here for reducing the harmonic torque. Okay, There are three methods, so these three methods we are going to see. The first method is very important. The first method which is very important mentioned here, that is the integral slot winding. Okay, we can say that the meaning is that when we are see the integral slot winding, so when we consider that, that is number of you can see over here, number of slots per pole per phase is equal to the number of fractional number. Okay, so if you consider that is number of slots per pole per phase, that should be equal to fractional number. In occur due to this, what happened is to create a symmetrical MMF distribution around the air gap. Okay, if this slots per pole per phase is equal to fractional numbers, then what happened, I will show you over here. If this is your rotor stator and if this is your rotor, so in between this gap is known as the, you can consider is the air gap. Okay, this is considered as a air gap. So you need to understand that this is stator and rotor, in between that there is an air gap will be there. Okay, so if the slots per pole per phase is equal to fractional number, so uneven or you can see asymmetrical MMF distribution around this air gap. So the number of slots, stator slots per pole per phase should be fractional number. That's what we need to understand. Okay, so I hope you will understand this. And there is one more thumb rule when we are choosing number of slots per pole per phase. There is one more thumb rule. It suggests that you have to calculate it roughly. We can say that if we should take the number of slots per pole per phase should not be greater than or should not be greater than 2. It should not be greater than, this slots per pole per phase should not be greater than 1 or should not be greater than 2. But in case of small motors, okay, so we need to understand generally for the motors or generally for the small motors that slots per pole per phase should not be greater than 2. Okay, so it can be considered as 3 or 5, or it is taken in the general value 3 or 5, which we considering 4 slots per pole per phase. Okay, in some numericals we considered this is the value considered as the value, that is slots per pole per phase is equal to 3 or 5. Okay, so further, another method to reduce the harmonic torque which is producing in induction motor, there is one more method that is called chording. Okay, this is called chording. Okay, so we discussed that internal slot winding. Now we discussed that chording. So over here for the chording, slots per pole per phase is equal to the integral number. What it is suggested? Slots per pole per phase is equal to the integral number. Okay, so over here we can see. Okay, so in this case what we have considered in earlier case, one more important and interesting method will be calling it as internal slot winding section. We see that slots per pole per phase is equal to fractional number to create a symmetrical MMF distribution around the air gap. It is responsible for that. Okay, and in the chording you can see slots per pole per phase is equal to the integral. So in this method we can see over here the number of slots per pole per phase should be integral number, like it was a fractional number we said in earlier part. Here it is an integral number. So integral number means what will be considering any integral where we could weaken the stator winding MMF, or so MMF of the stator winding will be reduced by means of chording method. Okay, so chording slots per pole per phase should be in integral number like it was a fractional number in earlier case. One more important and interesting method will be calling it as a skewing. Okay, another method is a skewing. What we are going to do in that, so in this method the rotor conductors are arranged such that they should have some angle there. Okay, you can see in this figure, you can see this conductor when you are joining over there, it is having some angle, it is not exactly the straight. You can see if it is straight it should be like that. Okay, okay, but it is having some angle over, it is having some angle over here. Okay, so when you are make a such kind of arrangement, you can see that is the rotor conductors, how that angle is produced, that is shown in the diagram. Construction of a rotor is shown here. Generally the bars should be such that they are parallel to each other. Generally what happens, there is a parallel to each other, but likewise instead of directly considering them straight and directly connecting them to end rings, these are the end rings. Okay, these you can consider, these are the end rings. Okay, so we can say this is first ending, second end ring, and this bar could be simply the straight bars. They start up connecting them the straight arrangement, but the rotor bars are slightly skewed, which they have slightly some angle. Okay, generally this diagram, if I am considering two end rings, they could be simply like these straight lines, but it should be not like that, it should be a skewing. So what exactly happens due to this arrangement? So with such kind of arrangement we are able to reducing the harmonic in that or we are reducing the harmonic torque in the three-phase induction motor. So such those three are the methods. With the help of those methods we can reduce the harmonic torque in the induction motor. First, that is the integral slot winding, shorting, and the skewing of the rotor. Okay, so I hope you understand very well all those things what I explained to you in this session. Now we will see what are the questions has been asked in GTU examination related those things. Okay, so these are the questions was asked in GTO examination. The first question, that is explain the effect of harmonic induction torque and harmonic synchronous torque on the performance of three-phase induction motor. So you can easily explain it, what is the effect of harmonic effect on a harmonic of the three-phase induction motor, which was repeatedly asked in 2012, 2014, 15 and 16. Okay, so one more question, that is give the rules of selecting number of rotor slots and induction motor. That's what we discussed in this video. That is what are the rules, those conditions you have to be explained in detail in this question. Okay, and the third question, that is state the rules for the selection of rotor slots, describe the methods for reducing the effect of harmonic torque. Okay, the third question is state the rules for the selection of rotor slots and describe the methods for reducing the effect of harmonic torque. So which was also a very important question in exam point of view. So those are the questions asked in GTU. So students, I hope you are able to give all those answers with the explanation given in this video lecture. Okay, so I hope you watch this video and able to understand all the concept of effect of harmonics on performance of three-phase induction motor. Okay, thank you very much. Or you can see the pattern of this question. That is first question, it is said that the effect of harmonic induction torque and harmonic synchronous torque on the performance of three-phase induction motor. So in that you have to discuss what is the effect exactly of the harmonics on three-phase induction motor. Similarly, in third question you can see the state the rules for the selection of rotor slot. So there is a combination of both the what are the rules of the selection of rotor slots, and then they have to ask, and they are going to ask, that is describe the methods for reducing the effect of harmonic torque. So sometimes in that way the question may be twisted, but you have to keep in mind the concept remains same. So if you understood it clearly, so you can easily able to give the answer even the question was twisted in the examination. Okay, so I hope you don't have any query in the examination regarding with this question and answer. Okay, thank you very much once again. Okay.